Einstein, 100 years ago, gave a recipe for a prediction of how you might be able to detect the kind of gravity that he described in his famous 1916 paper. To him, gravity was not a force of attraction between objects as Newton would have you think of it. Einstein said that gravity is the distortion in the fabric of space and time. Imagine that space is a giant sheet of rubber, and things that have mass cause that rubber sheet to bend, like a bowling ball on trampoline. If I have a massive object and distortion it deeply, it kinda falls into the distortion, so you're really just staying with the flow, just like the Earth goes around the Sun, because the Sun is very massive, causing a big distortion in the fabric of space and time. So now, if you have a disturbance in this fabric of space and time, it will emanate forth as ripples, moving at the speed of light, traveling across the universe, stretching and squeezing space and time. As we can see in this example, it's exaggerated a bit just to show you how it works, and these are what we call gravitational waves. If me and my friends started to dance around each other, would we also cause ripples? But that would be extremely small, practically indetectable. So you need something really massive, moving very fast to cause that ripple that can be detected. It works by splitting a laser beam and sending it in two directions. The beam has to travel precisely the same distance, and then they are reflected off mirrors and then they come back, so they cancel each other out and nothing will reach the light detector. But when a gravitational wave passes through, it kinda changes the distance every beam has to travel, so they won't cancel each other out and the signal will be detected. And so, black hole. Whereas black holes coalescing is what did it, and in fact in the last instant before these black holes coalesce, it is radiating so much energy, more than all the stars in the universe, but only did it for a quick fraction of a second, or enough to travel 1.3 billion years, came across the detectors and changing the length between the mirrors by stretching and squeezing. Can you imagine this? And by the way, how much the length changed as the ripple went across? A fraction of the diameter of an atomic nucleus. The effect of a gravitational wave is so minuscule and easily confused with random noise. They needed a smart data analysis technique to identify it by comparing the wiggles they measured before to the ones they expected from a gravitational wave. It's like being able to identify a song being hummed at a very noisy party.